Okay. So in today's lecture, we're going to define geostatistical processes, which are widely used in statistics to model spatial or temporal data that is evolving in some way over time or space, that is indexed continuously over some set, usually like a spatial domain or temporal domain as well. So geostatistical processes are stochastic processes that are, as I mentioned, defined continuously over space. I'll mention that here. So this is an informal introduction. If you'd like to get some more information about geostatistical processes, more than what I will present in this lecture, I have some references for you. So this is a general applied review . Can be found in the following references. The first one is Diggle. Et al., 1998. And the second one I recommend is by O.Chkrebtii. And he's a former faculty member in my department, although I never met him. He left our department before I started working here. So those are some nice practical references. For a more measured theoretic overview, more again than I will cover in this class, I refer you to the following text. And the famous text on this is the Adler and Taylor, Random Fields and Geometry. The title is Random Fields and Geometry. So those are some follow-up resources you can use. So a geostatistical process is encountered in many areas of spatial statistics or time series analysis. There are many examples one could think of. The first example might be the risk of exposure to pollutants, such as particulate matter, can vary continuously in space and can be modeled through a geostatistical process. Another example relates to temperature fields across regions. And for this, I will refer you to the R code with the following name in GitHub. It is temperature measurements Ukraine.r. So this is the name of the R script, which I've posted on GitHub. And if you run it, I've pre-run it here because it takes a couple of minutes to load. But what you see here is temperature collected at some monitoring stations around Ukraine. And this is obviously earlier in fall 2025, because I understand it's much colder there now. But as you can see, obviously temperature varies over a region. And we might hypothesize that there is an underlying temperature field, which we are observing at those particular points, which is defined continuously across the area of Ukraine. So right now in this lecture, we're just going to talk about how to define these kinds of geostatistical processes. And then in the following lecture, we'll talk about how to fit this type of discretely observed data to these stochastic process models. All right, so let's get to the definition of a geostatistical process. It's a stochastic process. We're going to denote it like this: is the set of random variables x indexed by some inputs t. So these could be, for instance, spatial locations. Where t is located within this geographical region, like Ukraine in the previous map I showed you. And that is a subset of Rp. In practice, P is usually 2 or 3, but of course, in principle, it could be any natural number. Okay. Of course, I want to mention a few things. This stochastic process is defined on an appropriate probability space. I think the discussion of that is beyond the scope of today's lecture, so I'll refer you again to that Adler and Taylor textbook. This is just an example. There are many good references on this. The other thing I wanted to mention is that the location T varies continuously in D. Which is a subset of some larger space Rp. And another point is that we can consider the spatial process to be an uncountable collection of random variables indexed by their location. So each of these x of t are random variables. Now, of course, just like with the temperature data that I gave as a motivating example, it would be natural to assume that the random variables x of t will be dependent. And it is also natural to assume that that dependence depends on the strength of the correlation, indeed, between x of t at two different locations might be governed by the distance between those locations. So, for example, when you're talking about temperature, oftentimes locations that are close together will have temperatures that are more similar, but there are also features like mountains and other features where you get quite a large change in temperature as you go from one location to another. So the dependence structure in a geostatistical process can be quite complex, and the goal of the statistician is to model this dependence process accurately and then, of course, to fit this model to data, which we'll see how to do in the next lecture. All right. So I'll mention this, that it is natural to assume that xt are dependent, and so we're going to model that dependence. And we'll do this through the covariance function, which I'll define in a moment. So I want to show you an example of 4 realizations of such a geostatistical process over a spatial domain, just a unit square domain. So in the R code that I will present next, which is called Gaussian process realizations.R. I'm going to show you 4 samples or realizations or draws from a specific geostatistical model, which turns out is actually a Gaussian process, and for my example. So let's have a look at this. I will run it. It will take a few moments to render because we are evaluating these geostatistical process realizations over a fine grid. If you have any questions about the code or how we go about sampling these, you will have some, you may ask Eric during the practical sections, but I will also provide some guidance on that in the second homework and ask you to recreate code that is similar and similar results. Here we go. Okay, so these are 4 realizations of geostatistical process. I haven't really told you the details about the specific, how I define the specific process, but these are 4 samples from this process. So a couple of things you need to see. So first of all, the domain here is just a unit square. S1 and S2 are the spatial input dimensions, like the elements of T, for instance, would be S1 and S2. And I didn't include the temperature scale here, but the green the green regions have a higher magnitude, and then the red regions have a lower magnitude. So you can see that there is some dependence between nearby observations. Sometimes it's they're positively correlated, sometimes they're negatively correlated. And of course, if we had a situation where we had, for instance, white noise, these types of plots or these realizations would be a lot rougher looking. So you would see a transition from, like a pixel that is very green to one that is red, for example, very distinctly. Whereas here you have some patterns which indicate that there is some kind of smoothly varying correlation structure between nearby random variables at different locations. So these are the kinds of models that we wish to fit to data. You can think of these as being, for instance, realizations of the temperature field that you get. Yes, that's a great question. So I just received a question. So these are sampled over space in this case. So each unit square you might think would be some spatial region that you might want to model temperature over. And this could be, for instance, like some kind of longitude, and then here you could have latitude, for example. Yes. Thank you. Mm-hmm. And you can probably see that in reality, this is often how things like temperature vary over time, over space. All right, so typically, practically speaking, we observe geostatistical processes at finite number of locations, just like I showed you on that map of Ukraine. And so common question of interests are the following. And these questions of interest, we are both interested in approaching them from a modeling perspective. So we wish to somehow, if we have some prior idea of how we could answer these questions, we can incorporate them into the definition of our stochastic process. And there also is the question, having observed this data at discrete locations, can we say something about what the answer to these questions might be? All right, so one question you might be asking yourself is, what is the average value of x of t across the entire spatial domain? So what is the average function over this field? And remember, D is some subset of RP in this case. What is the value of xt at a specific unobserved location? So we might be interested in prediction. And then the last question we might want to ask ourselves is, what is the covariance between the values at two locations, and how does it change when between different sets of locations, for instance, as a function of distance between locations or other factors? i.e., we might want the covariance of xt and xs for t and s and d. So those are some common questions we might want to ask. And so for this, we need to talk about two important components of geostatistical processes. First, what will help us to answer the first question is the mean function. And second, the covariance function, which will help us to answer the third question. The mean function of the stochastic process, this geostatistical process, xt, is the expected value of the geostatistical process as a function of spatial location. In other words, we could write it as m of t is the expectation of x of t for t in this domain. So the mean here is a function rather than a vector. In lecture 1, we looked at multivariate normal distributions, which were used to describe random vectors, that describe the distribution of random vectors. These geostatistical processes can be thought of as random functions. So you can think of this as being somehow a generalization of that idea. So now, instead of a mean vector, we will have a mean function. And similarly, instead of a covariance matrix, we will have a covariance function. The covariance function of this geostatistical process is defined as, we're going to call it C of t and s, and it will be the covariance between this random variable x evaluated at t and this random variable x evaluated at s. And then, of course, that will be the expectation of xt minus m of t, the mean function, times x of s minus m of s. And this is for t and s in D. So hopefully from this, you can see that the geostatistical process is a generalization of a distribution from distribution on vectors to distribution on functions. So now instead of having a mean vector, we have a mean function. Instead of having a covariant matrix, we have this bilinear function C. And this function has all those same, or the analogous properties, which we're used to seeing in a covariance matrix. The covariance function measures the strength of the linear dependence between two random variables and has the following properties. So here are the properties. First, we have a generalization of symmetry, like we had for those covariance matrices previously. Now we have that the covariance function is symmetric, like this. For all t and s in D. The second property is that when t and s are the same location, we now have that the covariance between these two, the random variables of these two locations, the covariance function is equal to the covariance between xt and itself, which is actually just the variance of xt. And the third property is that this function, see, this covariance function is non-negative definite. Sometimes we say it is just positive definite. The non-negative definite is there to generalize things a little bit and allow for variables x, which have, for instance, like a degenerate distribution. Like, for instance, if we were looking for at a Gaussian process. We'll see that in a second. In the next lecture, when we fit these models to data, we're planning on interpolating some data. Of course, we want that variance to be 0 at a specific location. And so a non-negative definite covariance is desired. There were some questions in the last lecture about the degenerate case. And so this is one assumption that enables that degenerate case. And it was also mentioned in the previous lecture that the positive definiteness, and indeed the non-negative definiteness, is a requirement of this specification of the covariance function as a covariance between x and t and x of s. I'll pause here for a second and see if there are any questions. And I'll be happy to answer some questions too after class. All right. So next, we're going to define some specific types of geospatial stochastic processes, specifically stationary processes. A geostatistical process x of t, t and d, is called stationary if the mean function is constant over the spatial domain and the covariance function only depends on the displacement between the points. So I will write this down mathematically as follows. So the first requirement is that the mean function is constant for all t and d. And 2, the covariance function only depends on the displacement between the points. This is what I mean. The covariance function depends only on the amount of displacement between the two spatial locations. So the covariance, the dependence between two random variables x at two different locations depends only on their distance from one another. There is another important definition of an isotropic process. Isotropy is when the covariance function only depends on the distance between t and s, the two spatial locations. But of course, an isotropic geostatistical process must be stationary. So a stationary geostatistical process is isotropic when the covariance between S and T depends only on their distance. So the dependence is the same between any 2 points in your domain, okay, as long as they have the same distance between them. In other words, the relative location doesn't really, or their location, sorry, their absolute location doesn't matter as long as the relative locations are fixed, or the dependence between, or the distance between the two is fixed. And this denotes the norm between the two locations, T and S. Typically, we use a Euclidean norm here, but it could really be any type of norm. Now, if the covariance function of the stationary process depends on both the direction and the distance between the locations, then the process is called anisotropic. These distinctions are important to keep in mind when modeling. So in applied statistics, we often have to propose a probability model describing how we think a particular process is evolving over time. And usually we need to account for the characteristics of the process that are known, such as isotropy, such as stationarity, smoothness. We'll talk about smoothness very soon as well. All right. Okay, so next I will indeed talk about the smoothness of a stochastic process. So that's something else we need to keep in mind when doing statistical modeling. We will get to Gaussian processes in a moment. So as with deterministic functions, there is a notion of smoothness, a notion of continuity and differentiability for these kinds of geostatistical processes. But we look at these properties in the mean square sense. Okay, so we're going to define here these mean square properties of mean square continuity and mean square differentiability. So I'm going to first provide the definition of mean squared continuity. A stochastic process or a geostatistical process, but in fact, any stochastic process, let's say geostatistical here, is said to be mean squared continuous, mean square continuous if the expected value of the squared difference between the process at time t and a nearby point at time t plus h vanishes as h tends to 0. Another way of thinking about this intuitively is that mean square differentiability implies the process does not have jumps on average in an average sense. Okay, let's restrict our view here to a one-dimensional input t just for simplicity, but of course we can generalize this to a different number of dimensions. So let's see here. X is mean squared continuous if the limit as h tends to 0 of x t plus h minus x of t squared is equal to 0. Okay, so this we're going to assume is in one-dimensional space. So we're going to assume here d is on the real line in this case. And then the definition for mean squared differentiability is exactly what you would expect. And of course, when d is in a higher dimensional Euclidean space, we can, of course, use directional derivatives to define mean square differentiability. If there exists process d dt of x of t such that the limit as h tends to 0 of the expectation of the square difference between x t plus h and xt divided by h minus this derivative is equal to 0. Right? So what this means is that there exists a process that acts as a derivative in the mean square sense. So that's what it means for a stochastic process, particularly a geostatistical process, to be smooth. Let's provide a very brief example, a well-known example. So one well-known example is the Brownian motion. Which is well known to be mean square continuous everywhere. But mean square differentiable nowhere. And this can be shown by looking at its autocorrelation function, and noticing that it's not differentiable along a particular direction. So now that we have introduced different properties of geostatistical models, we can now go ahead and formulate a Gaussian process. A Gaussian process is a special type of geostatistical model, and it can be viewed as a generalization of the multivariate normal distribution, which I reviewed in the first lecture. So in a sense, we're generalizing a distribution over random vectors to a distribution over random functions. Can be interpreted perhaps by better wording. As a generalization of the multivariate normal distribution from vectors to functions. This is what a Gaussian process is mathematically. Let's define it. The geostatistical process x of t, t in d, is a Gaussian process if the joint distribution of any collection of random variables has a multivariate normal distribution. So it is a special kind of geostatistical process, which is very easy to work with from an applied sense. One important feature of a Gaussian process is that it is completely specified by its mean and covariance function. This should not be surprising because as a generalization of the multivariate normal distribution, which is also defined by its mean vector and covariance matrix, this is expected. I'm going to use the shorthand GP for Gaussian process. So a Gaussian process is completely determined or specified, I should say, by its mean and its covariance function. The mean function m of t is the expectation of x of t. And 2, the covariance function oh, I'm sorry, this should be s here. So once these are specified, we have uniquely, well, once we have provided the mean and covariance, we have uniquely specified the Gaussian process's distribution. Okay. We write the Gaussian process model as follows. So we'll say that x, or x of t, if you like, follows a Gaussian process distribution. Some people will just write normal, but others will write Gaussian process here, or maybe it's easier if I write it this way, GP, specifying its mean function and its covariance. Maybe I should just write it this way. All right. So as I mentioned before in the definition, any finite subcollection of these x's should follow a multivariate normal distribution. So by the definition, the probability density function or PDF of this vector x here that is obtained by taking a finite, joining together a finite subcollection of random variables x is given by f of t, of x. This is just the density of the multivariate normal distribution with mean vector m and covariance matrix C, which are defined, will be defined in a moment. So here, M, this vector M, is given by the corresponding evaluations of the mean function M at this subset of locations T1 to Tn, and the covariance functions, and the covariance function has jkth element covariance matrix. C is this covariance function evaluated at Tj and Tk. Okay. So now you can see why the covariance function have to be non-negative definite, and of course the mean does not have a restriction.
Sorry, non-negative is enough?
Yes, that's right. That's right. So in the previous lecture, we mentioned that covariance function should be positive definite. For the, covariance matrix. The covariance function can be non-negative definite because we are allowing for the degenerate case. So you can have a degenerate multivariate normal distribution, which has a variance of 0. So we call that a degenerate distribution. Its density is a Dirac delta, a point mass. So yes, we are.
When they say semi-positive definite.
I'm sorry?
There's no PDF. Semi-definite.
Oh, yes, yes. I'm sorry. Yes, yes, that's right. That's right. So yes, maybe I misspoke here. Right. So the covariance has to be non-negative definite.
Okay.
Yes. Thank you. Sorry, I think I misspoke earlier. Okay.
Thank you very much.
Great. Right. Okay, perfect. So this is a Gaussian process, and I'm going to next talk a little bit about different covariance functions. So the mean function can really be just about anything, any kind of function. The covariance matrix, has to have this restriction. So there are some classes of covariance matrix that we use a lot in practice. One of these Gaussian process covariance functions is the Matern class. So I'm going to show you what that looks like, and I'm going to relate the choice of hyperparameters or constants here that are parametrizing this covariance function to the smoothness, the mean square differentiability of the resulting Gaussian process. So there's many different types of models, but one very common example is the Matern class. And then it looks like this. It's a flexible class of covariances. And as I mentioned, we can relate the choices of these hyperparameters L and nu here to the smoothness of the resulting Gaussian process. All right, and in this specification, K is the modified Bessel function of the second kind. Capital gamma is the gamma function. This is the Euclidean norm. The norm here is the Euclidean norm. We also have two parameters here. L is the length scale parameter. If you ever talk to someone who is an oceanographer or deals with, for instance, models of ocean currents over the Earth, they often refer to this length scale parameter as a decorrelation scale because it essentially controls the rate at which correlation decreases with distance between points in the input space. So as you can imagine, for many real world processes, as you get further and further away, the correlation between those two random variables will decrease. And so L controls how quickly that decrease occurs. And we'll see a figure of that in the next R code. Okay. And this parameter here, this new, oh, of course, L, I'm sorry, I forgot to mention that L has to be greater than 0. It lives on the positive real line. And the smoothness parameter also lives on the positive real line. It controls, this is the smoothness parameter. Controls the mean square differentiability of the resulting GP, Gaussian process. So you can see why this is a really nice class of covariance structures, because you can directly adjust the decorrelation scale, this length scale parameter, but you can also directly adjust the smoothness parameter as well. This covariance family also contains a very commonly used covariance structure called the squared exponential. Squared exponential, and its a limiting case. As the smoothness parameter tends to infinity. And this covariance, the squared exponential covariance, looks like this. It is the exponential of the negative norm between t and s divided by the L2 norm, and divided by twice the squared length scale. So you can see here that the correlation decays with the length scale even from this specification. Turns out that for a zero mean Gaussian process with a squared exponential covariance, the variance of the jth partial derivative is 2 over L squared. So the variance is related to this length scale parameter. And larger length scales correspond to smaller variation in the derivatives, resulting in smoother realizations. So the example that I showed you earlier in my R code of those 4 different realizations of a geostatistical process, those were obtained using a Gaussian process with a squared exponential covariance and a chosen length scale. So if you look through the code, that's exactly what it is. So you'll see that I defined a squared exponential covariance and I simulate the Gaussian process. The way I simulate this Gaussian process, of course, is over a finite, very fine grid by using this multivariate normal property, so that any finite subcollection of from this geospatial this Gaussian process is a multivariate normal set. So I actually just sample from a multivariate normal distribution over this very fine grid across the domain. And so those figures that you saw earlier, these realizations are drawn from a Gaussian process that has a squared exponential covariance. So you can see that the realizations are quite smooth themselves. And that's what we expect for a squared exponential covariance. Okay. And then the next thing I'd like to show you is the code called Matern, GP samples, and smoothness. And this will show you some realizations of 3 different Matern Gaussian processes, each one having Matern covariance and zero mean. And the Matern covariance will have different smoothness parameters. So nu is going to be different. So in the first case, the smoothness parameter is equal to 1/2. And you can see that the realization of this Gaussian process, now the input here, I should have labeled this t rather than x. And this f of x is x, actually. So I apologize for the slightly different notation. But so this blue line here is a realization of a GP with a Matern that has the smoothing parameter set to 1/2. So it's quite rough, as you can see. And if you look at this other plot right here, you can see the covariance as a function of distance between the 2 points. So this is indeed a stationary geostatistical process. And on the x-axis, we have the input distance. So as the distance increases, the covariance between 2 locations that are separated by that distance is decaying rather quickly, as you can see here. Now, when we set the smoothing parameter nu to 2, we see this realization as the red dotted line is much smoother than the blue realization. So indeed, this Gaussian process from which this realization comes has more mean squared derivatives than the previous Gaussian process that we looked at. And indeed, you can see here that the covariance for the red process is decaying in a much slower fashion as a function of input distance than for the case when nu is 1/2. And then the third case we're going to look at is the squared exponential covariance. So we're going to take the limit as the smoothing parameter tends to infinity. And so what we end up with is a squared exponential covariance, which is gives rise to very smooth Gaussian processes. The realizations are extremely smooth, as you can see here. And if you look at the rate of decay of the covariance with the input distance, you see that the rate of decay is rather slow. All of these covariances have the same length scale, in order to be able to compare the rate of decay. Of course, the length scale will determine, relatively speaking, how quickly these will decay. But given the same length scale, you should be able to see quite a big difference in the three. Okay, so I think I'm going to end the lecture here. We will talk a little bit more in the next class how to fit these models to data.